Chapter 5, I'm going to talk about gases. You are able to breathe because of how gases behave. You can do a calculation, and in a given day, you move about 8,500 liters of air in and out of your lungs, and you don't even think about it. You're just breathing. Air going in and out. And breathing is possible because of pressure differences. So what is pressure? Well, we all know, I'm sure a lot of you feel under a lot of pressure being in school, right? You're like, I've got all these deadlines, and you get out into the work world and you've got different sorts of pressure. That's not the sort of pressure we're talking about. Pressure in science is defined as a force per unit area. So gas molecules exert a force on surfaces as they run into them. Now, is that a very large force? No. Gas molecules, being molecules, are incredibly small. So when they hit something, it's not going to be much at all. But there's so many of them that when they hit surfaces, it does matter. It does add up, and the gas pressure is significant. How much pressure a gas exerts is going to depend on several different factors. First of all, the number of gas particles. So I kind of think of a gas particle exerting a force. You think of a little tiny gas particle like running into the chalkboard, right? Just barely, nothing. It's a little bit like a one-year-old kid punching you in the stomach, right? A one-year-old, they're just not very strong. And it's like, oh, I felt that, but that didn't hurt at all, right? But what if that happens over and over and over and over again? You might get sore. Or if they all hit you at the same time, right? So more gas particles, more pressure, right? The volume of the container matters because it's force per unit area, the pressure is. So have you ever seen those guys that can walk on beds of nails? Like, how the heck can they do that? If you stepped on one nail, what would happen? I think a lot of us have had that happen. It goes into your foot. So how can you walk on a bed of nails? Well, it's spread out. There's a bunch of nails. You can't walk on one nail at a time, but if you have a whole bunch of nails very close together, when you step on it, the pressure gets spread out over a larger area. Okay? It's a little bit like, say, your 14-year-old son, you're laying on the floor. I don't know why I would be laying on the floor. But you're laying on the floor, and your 14-year-old son comes and lays on top of you. And you're like, I feel pressure. He's heavy, right? But it's not that bad. But if he steps on you with just one foot, that's going to hurt a lot, right? Same amount of force. His weight is the same. But if it's spread out over your entire body, the pressure isn't so bad. If it's concentrated in one small area, then the pressure is greater. So if the volume of the container is larger, there's more area and the pressure gets diminished because the area is larger. The force is the same, the area is larger. And then we have the speed of the particles. So the force that the individual particle exerts is going to depend on its speed. If it's moving faster, it's more force. The average speed of the particles is not going to affect the area, but it's going to affect how hard they hit. It's also going to affect how often they hit. Okay? So what happens when you inhale, your body is increasing the volume of your lungs. That causes a decrease in the gas pressure, the gas concentration. So your lungs are the container. When you increase the volume, that causes the pressure to go down. There's constant pressure outside. Your nose, your nasal passages are open, and so the pressure outside pushes air into your lungs. And then what do? You exhale. You squeeze it back out. I think I got ahead of myself. No, I think it's just not even in there. They're just going to leave us holding our breath. So you inhale, air comes in. When you exhale, you decrease the volume, you increase the pressure of the air, and that causes it to go out. Repeats. Air pressure changes also create weather and help us to predict what's going to happen. So here's an example of a pressure map, a low pressure region here, a high pressure region there. Meteorologists study the patterns, and they've come to the conclusion that high pressure is usually associated with clear weather, and low pressure is usually associated with unstable weather. You get a storm or a lot of wind, something's going to happen. It's differences in pressure. The number of gas particles in a given volume of air changes with increasing altitude. So as you go higher above sea level, the number of particles in a particular volume of air gets smaller and smaller and smaller. What does that do to the pressure? Fewer particles. Pressure goes down. So the air pressure is lower at high elevations. So here we have two, those look like mason jars, not very scientific. Two mason jars. This one has fewer gas particles in it than this one. And you can tell just by looking at them, this looks more concentrated, right? More particles in a given volume, and this is less concentrated. This is going to have a higher pressure, and this will have a lower pressure. It also affects the density. If you have more particles, those particles have mass, and density is grams per milliliter, right, is what we've talked about. Well, if you have more particles in the same volume, the density is going to be larger. Pressure also explains what happens to your ears when you go, say, up to Grant Grove and then come back down, or you take a flight in an airplane and you go up and your ears pop, right? So inside your ear, you have an eardrum that separates the outer ear from the inner ear. And this vibrates and stuff, and that's what enables you to hear. The inside of your ear is connected through your eustachian tubes down into the back of your throat. When you go high in elevation, the air pressure outside of your eardrum is reduced. Higher elevations, fewer gas particles, lower pressure. Inside your ear, you have air, and that's at the same pressure it was before you went up the mountain, and that's going to put pressure on your eardrum and cause your eardrum to bulge out. That's not pleasant, and it makes it hard to hear, too. So when you yawn or chew gum, that helps your eustachian tube to open up and let the pressure equalize. The opposite thing happens when you come back down. Then you have low pressure on the inside and higher pressure on the outside as you come back down into the valley. Then your ears have to pop and equalize the other way. Any questions? When the openings to your eustachian tubes are in the back of your throat, and so when you yawn or swallow, that helps them to open up. And that's why if you have a bad cold and everything is congested in your head, your eustachian tubes are not going to open up very well, and that's when it can really, really hurt. Babies have very, very small eustachian tubes, and that's why babies often scream on airplanes. Their ears hurt. They're not doing it just to make us crazy. I love it when science explains stuff that happens in everyday life. Well, how do we measure pressure? There are different sorts of pressure gauges, but one of the earliest ones was the Mercury barometer, and this was used to measure atmospheric pressure, the pressure of the air around us. Do you feel like the air in this room is putting pressure on you? No? No. Because we feel it all the time. And if we didn't have it, we would react, we would feel like it was negative, right? We'd feel the loss of pressure. So the original mercury barometers looked something like this. It was a dish of liquid mercury, and they took a long tube of mercury and inverted it into the dish. And then some of the mercury comes out, but most of it remains in the tube. And that in itself is a little mysterious, isn't it? How does that happen? Because if I just tipped this upside down and I didn't have the dish underneath, what would happen? All the mercury would run out. And then we'd have a hazardous situation on our team, and we have to call the hazmat team, and blah, blah, blah. That's why we don't use mercury barometers anymore. What's holding the mercury up in this tube is that atmospheric pressure is pressing down on the mercury here. Gravity is pulling down on the mercury in this tube and trying to get it to come out, but the pressure of the atmosphere is pushing here and supporting it. So the height of this column of mercury is directly related to the atmospheric pressure. The original experiments, because people didn't know what pressure was, they didn't know what molecules were, they didn't know what made up a gas or anything. A guy named Torricelli made a barometer like this and walked up a hill with it, a mountain, a small mountain. And he noticed that as he went up, the column of mercury got shorter and shorter and shorter. Interesting. And then you come back down the hill, and the column of mercury gets taller and taller and taller. What's going on? Some of these early guys, I mean, they were geniuses. There was no electricity. I mean, people didn't know anything, and they're making these observations and figuring stuff out. Chemical history is really fascinating. So, average atmospheric pressure at sea level is going to support a column of mercury that is 760 millimeters tall. You can do length unit conversions and convert that to 29.92 inches. And so that is a unit of pressure. A length of an element is a unit of pressure. That's weird, huh? It's because of how this was made. So the height of the column of mercury measured in millimeters is a pressure. So that is equivalent to 1 atmosphere of pressure. So they did give that unit a name. They named it after Torricelli, so they call it 1 torr. So 1 torr is exactly the same as 1 millimeter of mercury. I think the hope was that we would all just use torr and forget the millimeters of mercury. Didn't happen. Now we've just got 2 units to be confused about. Any questions? I'm rambling. Yes?
When I was reading the book, they gave us like a lot of different units that so you could like long versions. Are we gonna have to know all of them?
You're not going to have to know all of them. No. There are lots of different units in the book. Maybe some of these units, right? The reason we have lots of different units is they're useful in different situations. So the Pascal, that is an SI unit of pressure. It's 1 Newton per square meter. The abbreviation is PA. Chemists don't use it much. But other areas of study use it. It's a very, very metric unit. The average pressure at sea level is 1 atmosphere. And so 1 atmosphere is equal to 101,325 pascals. You don't have to remember that number. You may be more familiar with PSI. If you've ever had to check the pressure in your tires, in your car, your bike, it's measured in PSI. PSI stands for pounds per square inch. Remember, pressure is force divided by area. Well, pound is a unit of force, and square inches is a unit of area. Just like Newton is force, square meters is area. So, atmospheric pressure is 14.7 psi. And then we have the torr. Torr and millimeters of mercury, exactly the same thing. abbreviated torr. 1 atmosphere is exactly 760 torr. Because really, the atmospheric pressure at sea level, it kind of varies all the time, right? And so they had to just decide, what's it going to be? So they decided 760. So when you're doing sig figs, 760 is an exact number. The rest of these are not. The 14.7, that's not exact. And here in inches of mercury, 29.92. And the unit we use a lot in chemistry is an atmosphere. It's abbreviated ATM. 1 ATM is 760 torr. So which ones do you need to know? You need to know torr, millimeters of mercury, and atmospheres. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr. Memorize. It's not that hard. The others, if you need them for a conversion on an exam, I'll give them to you. This is how those units are often presented rather than what's in the table. And the reason they're put this way is because all of these are equal to 1 atmosphere. You can convert between any 2 of them in 1 step. You don't have to have a series of this to that to the other thing. All of these things are equal. So the weather report says the barometric pressure is 30.44 inches of mercury. What would that be in PSI? This is going to be 1 step. 30.44 inches of mercury. I'm going to have 1 factor. I want PSI on top. I want inches of mercury on the bottom. There's that dimensional analysis again. So I go to my table and I see 14.7 PSI. Okay. And here I've got 29.92 inches of mercury. Those 2 are equal. This is equal to 760 torr. That is equal to 1 atmosphere. 760 millimeters of mercury equals 101,325 Pascal. 29.92. .44 times 14.7 divided by 29.92. I think 29.92 has a nice symmetry to it. How many significant figures should that have? 3. Because your book chose to give this as 14.7, it's 14.69. We could have another sig fig. Oh well. So then we would round that and call it 15.0 PSI. Any questions? So here's a trick question for you. Your car tire is flat because some idiot came and slashed it. There's this big gash in the side. What's the pressure inside your flat tire? 1 atmosphere. It's the same pressure as outside. So about 14.7 PSI. Instinctively, you want to say 0, right? It's 0 above atmospheric pressure, but it's not actually 0. Barometer measures atmospheric pressure. What if we want to measure pressure in a container? We use a manometer. That always, it's like, I took Spanish in high school, so I know just enough to be really dangerous. Mano, right? Hand? Is this a hand meter? Does it measure your hand? No, manometer. It measures the pressure inside a container. So here's a very simple manometer. A tube that's shaped like a U. We always called these U-tubes, but that's something else now. And it's got mercury in it, and you attach one end of the tube to the container that you want to measure the pressure, and the other end of the tube is open. Now, if both of these were open to the atmosphere, the mercury would sink to the bottom of this U-tube, and the levels would be equal, right? Here, this is a high-pressure gas. It's putting pressure. It's pushing this side of the mercury down, while gravity and atmospheric pressure are pushing this side down. Actually, gravity's acting the same on both. Atmospheric pressure is pushing down over here. Well, in this case, the pressure inside is winning. It's stronger than atmospheric pressure because it's pushing the mercury away. So we can measure the pressure in here by looking at the difference in the heights of these columns of mercury. This is crazy low-tech stuff. A tube with mercury and a ruler can measure pressure. We would take this height in millimeters of mercury and add it to what the atmospheric pressure was that day in millimeters of mercury, and that would give us the pressure inside.